Hello everyone, my name is John Owaneka. I'm a student at the Yale University. My supervisors are Yajin Liu and Rebecca Harrington. My talk today is on our study on the relationship between earthquake B values and differential stress in the Challenger seismic zone in eastern Canada. I'll begin with a little bit of background information. This figure here shows a variety of faulting styles that reflects the relative magnitude of the three orthogonal principal stresses acting on the region. That is one vertical and two horizontal stresses. We get normal faulting if the vertical stress is the largest, strike slip faulting if the vertical stress is intermediate, and truss or reverse faulting if the vertical stress is the smallest. These stresses are clearly paramount in our understanding of earthquake processes. At shallow depths, the magnitude of these principal stresses are commonly measured in situ, for example, with borehole breakouts. However, at greater depths, in situ measurements are impractical, so indirect methods such as stress inversion with focal mechanism data are used to estimate the relative magnitude of the three principal stresses. Another piece of information that is considered in this study is the Gutenberg-Richter relationship. For the most part, earthquake size distribution follows this power law relationship. The slope of this power law describes the relative occurrence of small and large events, and it's referred to as the B value. Low B value indicates a larger proportion of larger events, whereas a high B value indicates a larger proportion of smaller events. Now, given that seismic activities are governed by fault strength and prevailing stresses, an important question is raised on what the frequency magnitude distribution, that is the Gutenberg-Richter relationship, can tell us about stress conditions. Several researchers have studied the relationship between B value and physical mechanism. For example, Chelema et al. 2005 found a systematic dependence of B value on earthquake focal mechanism where thrust, strike slip, and normal faulting events have smaller, intermediate, and larger B values, respectively. Mori and Abercrombie 1997 found that B values decrease linearly with depth and interpreted the observation as a B value dependence on material heterogeneity. Some others, for example, shows 2015 found that B values inversely correlate with differential stress, and this relationship is supported by laboratory experiment, and we explore it in detail in this study. In order to further explore the dependence of B value on differential stress, we must first determine the magnitude of the principal stresses, or at least a representation of their relative magnitude. R is a representation of the relative magnitude of the three principal stresses, and it can be determined from stress inversion. R decrease with decrease in the difference between the maximum and intermediate stresses, and or increase in the difference between the maximum and minimum stresses. The denominator of R, that is sigma 1 minus sigma 3, is the differential stress magnitude. Now, let's look at some differential stress relationships. For an optimally oriented brittle fault, Zuback and Town in 2001 determined a theoretical relationship that indicates differential stress increases with depth. Field observation in the Canadian Shield show the three principal stresses all increase with depth. Empirical relationship derived from the field observations indicates a linear relationship between differential stress and depth. This linear relationship agrees with the theoretical relationship. Now, given that the differential stress is a term in R, we will use R as proxy for differential stress and probe how R value relates with B value. A little bit of introduction of our study area. The Challenger seismic zone is located in eastern Canada within the St. Lawrence Paleo Reef system. The pre-existing southeast dipping normal faults, for example, the Gouffre River, St. Laurent, and Charlevoix faults, are overprinted by a late Ordovician to early Silurian meteorite impact, measuring almost 60 kilometers in diameter. About 180 earthquakes are reported every year in the region. And this figure here shows the almost 6,000 earthquakes reported in the Charlie seismic zone between January of 1985 and May of 2020. So our objective in this study is to, one, determine how B values excuse me, is distributed in the Charlie seismic zone. Two, determine the orientation of the principal stresses and the stress ratio in the area. And three, explore the possibility of a relationship between B value and stress ratio. So let's explore the first objective. Now, to calculate the B values, we use relocated seismicity of URL 2016 and Olmec era 2018. The seismicity in the Charlevoix region is diffuse, so we use our probabilistic clustering technique, the Gaussian mixture model, to divide the region into spatial clusters. Gaussian mixture model clusters data points to a predefined number of Gaussian distribution, and the algorithm calculates the probability of a data point being part of all the clusters, but assigns the data point to the cluster of the highest probability. Now, we calculate B values for each cluster using the maximum likelihood method. This figure here shows the map view of the 3D spatial clustering. Now, each cluster represents a grouping of events that are spatially connected and share common characteristics. Now, the color-coded numbers represents B value of the respective clusters. Next, we make profiles to more clearly show the spatial distribution of the events and the clusters. When you look at the map view, you would immediately notice overlaps in the clusters, but from the cross-section, it becomes more clearer that the clusters are spatially connected but distinct. In these figures, there are two families of clusters, one for earthquakes within the upper 18 kilometers, that is the red and the yellow clusters, another for the deeper earthquakes, that is the blue and the green clusters. Majority of the events occur within the upper 18 kilometers, and that's within the impact structure. So these clusters highlight what might be interpreted as somewhat different physical conditions. For example, denser fracture network within the upper 18 kilometers resulting in more diffuse seismicity. The B values all fall within the typical range of tectonic earthquakes, that is, they are close to 1. The average B value in the upper clusters is 0.8. In the lower clusters, average B value is 0.7, slightly lower than in the upper clusters. This decrease in B value with depth is in agreement with previous studies. Next, we investigate stress ratios and orientations of the principal stresses within these clusters. As I mentioned earlier, in situ stress measurements are impractical for greater depth, as middle class and deeper. So we use focal mechanism solutions to invert for stress ratios and orientation. We calculated 161 focal mechanism solutions for events of magnitude 1.3 and above. We augment our data set with 64 focal mechanism solution data from Mazzotti and Townend 2010. The figure on the left is a map view of the focal mechanism solution color-coded by the clusters. On the right, we show the distribution of the faulting style in each cluster. This faulting style distribution plot shows that the events are predominantly truss faulting events. Here we show the stress inversion results. These are busy figures, but I will explain everything in detail. In the figure on the left, the black converging arrows show the azimuth and mode of the regional stress inferred from in situ measurements within the upper 2 kilometers. The orientation of the three principal stresses from the stress inversion, represented as blue for minimum, green for intermediate, and red for maximum stress respectively, is shown in the stereo nets. The color-coded number indicates the azimuth of the maximum principal stress within the respective clusters. On the right, the stereonaires are plotted on the cross-section. The results show that the maximum principal stress in the Challenger seismic zone is rotated clockwise from the regional stress direction. The eastward rotation of the maximum principal stress is more in the lower clusters than in the upper clusters. And the stress rotation suggests that the main source of stress perturbation is different from the source of the regional stress. Now, let's find out what might be responsible for this stress rotation. On the left, we show the orientation of the maximum horizontal stress in each of the clusters. On the right, we show a figure from Tayoun et al. 2018. The authors looked at GPS trend variation in the St. Lawrence Valley. Broadly, the GPS horizontal velocities show similar trend of rotation from the regional stress. And the deformation recorded by this GPS is suggested to be from postglacial isostatic adjustment following the Wisconsin glaciation. Now let's take a closer look at the GPS horizontal velocities field in the Charlevoix area, that is within the red box. From this close-up view, we see strong local variation, but most of the horizontal velocities show southeast trend, which is an eastward rotation from the regional stress direction. The GPS horizontal velocities fields show deformation primarily driven by postglacial isostatic adjustment, which indicates that the stress rotation observed in the Charlevoix seismic zone is driven primarily by stress perturbation from the postglacial isostatic rebound stresses. Next, we put all this information together to establish if a relationship between the differential stress and B value in the Charlevoix seismic zone exists. The existence of such relationship would suggest that B value could serve as stress meter proxy for the Charlevoix seismic zone. This figure shows the relationship between B value and R as a proxy for differential stress. These observations are few, nevertheless, they show an inverse relationship between B value and R, which again is a proxy for differential stress, which makes the case for the use of B value as a stress meter proxy. This result agrees with several other studies on this subject, including laboratory studies and field observations studies for a variety of tectonic settings. In conclusion, we find that B value in the Charlevoix seismic zone range from 0.1 to 0.87, plus or minus some error, and decrease with depth. We also find that the maximum principal stress is oriented roughly east-west, hence facilitates a reverse sense reactivation of the northeast-southwest trending normal faults. And finally, we find that the B value linearly correlates with stress ratio, indicating an inverse correlation with differential stress, suggesting a potential for use as a stress meter proxy in the Charlevoix seismic zone. Thank you.